Okay, so today we're going to be looking at period 3 for A-level chemistry. So to start off with, we got sodium reacting with water. This is the equation. It forms sodium hydroxide and hydrogen gas. And this reaction is vigorous since only one electron needs to be removed from sodium to form the sodium ion, and that requires little energy. The sodium melts into a ball on the surface. And then other observations is that there is effervescence and a yellow flame, and the solution has a pH of 12 to 14. Okay, so the other metal we need to know about is magnesium reacting with water. This is the equation. Forms magnesium hydroxide and hydrogen gas. In comparison to sodium, this is very slow, since 2 electrons need to be removed, and that requires lots of energy. And from atomic structure, you should know that the second ionization energy is bigger than the first, since you're removing an electron from a positive ion. And yeah, there's no visible reaction. The pH of the solution is 9 to 10, whereas sodium was 12 to 14, and this is because magnesium hydroxide isn't very soluble in water, so there's few hydroxide ions released. Now, this reaction is magnesium with steam. As you can see, the water is gaseous. The product here is magnesium oxide and hydrogen gas. Wait 1 second. Shouldn't be 2 here. Yeah, okay. And this reaction is much faster with steam compared to liquid water because there's more energy. And the magnesium oxide is a white solid. And there's also a white flame. Okay, so now moving on to reacting with oxygen. We've got sodium here, forming sodium oxide. This is vigorous and forms a yellow flame. Magnesium reacting with oxygen. This is also vigorous and forms a white flame. Now we got aluminium with oxygen. Now for regular aluminium, this reaction is slow and there is no flame. But if you use aluminium powder, it's much faster and there is a white flame. So moving on to the other elements, we got silicon, and this is slow and there's no flame. Oh, sorry, a white flame. Got phosphorus. The phosphorus spontaneously combusts and there is also a white flame. And for sulfur, forming sulfur dioxide, it burns steadily and there's a blue flame. And there's also sulfur trioxide, formed from sulfur dioxide. Ooh, it should be a half here. Yeah. This uses V2O5 catalyst and a high temperature, but we will look at that reaction in a later topic. And all the solid products in these reactions are white, whereas all the gases, like sulfur dioxide and sulfur trioxide, are colourless. Now let's look at the melting points of the oxides. The metal oxides are ionic, so have high melting points. There's a strong attraction between the ions, needs lots of energy. Magnesium oxide is higher than sodium oxide, as the magnesium ion is more highly charged and is smaller. This means there's a greater attraction between the magnesium ion to the oxide ion. Now you might think aluminium oxide will be higher than magnesium, but it's actually lower, and that's because the aluminium ion has a high charge density, so it polarizes the oxide ion, so there's partial covalent bonding, which means it's lower. So now moving on to the non-metal oxides. Silicon dioxide is very high since it's a giant covalent molecule. Strong covalent bonds between atoms, needs lots of energy to break. P4O10 and SO3, they're simple covalent molecules. So they've got weak intermolecular forces, which need little energy to overcome. And the phosphorus oxide is higher than sulfur trioxide, since the phosphorus one is a larger molecule with more electrons, so there's stronger van der Waals forces between molecules. Okay, now we're looking at the reactions of the oxides with water. So sodium oxide with water forms sodium hydroxide with a pH of 12 to 14. Magnesium oxide forms magnesium hydroxide, pH 9 to 10. These metal oxides, they're ionic, so they form alkaline solutions. This is because the lattice breaks down to release oxide ions, and the oxide ions accept protons from the water to form hydroxide, which makes it alkaline. And as we said before, magnesium hydroxide is not very soluble, so that's why the pH is not as high. So let's look at the other oxides. Phosphorus oxide forms phosphoric acid with a pH of 0 to 1, and the acid is strong. SO2 forms H2SO3 with a pH of 2 to 3, and the acid is called sulfurous or sulfuric 4 acid, where that 4 represents the oxidation state of sulfur, and that acid is weak, so that's why the pH is a bit higher. And sulfur trioxide forms sulfuric 6 acid with a pH of 0 to 1, and that is a strong acid. So these non-metal oxides from the last slide, they are simple covalent and they accept protons from the water to form an acid, and these acids then break down to form H plus and a conjugate base. So these are the structures of the acids. Phosphoric is tetrahedral. Sulfurous is trigonal pyramidal, and sulfuric is tetrahedral. And you need to just memorize these. And for the anions, as in the base is formed, you remove a H atom and the oxygen becomes negative, and the acids dissociate in stages. So you could have one H removed, then two, then three. Okay, let's look at some more oxides. Silicon dioxide is insoluble in water because it's got very strong covalent bonds between atoms. And the water cannot supply enough energy to break them. However, it is still classed as acidic since it reacts with bases to form salts. Aluminium oxide is also insoluble in water because it has a high lattice enthalpy. However, it is classed as amphoteric because it has the properties of both an acid and a base. So For this last slide, we've got reactions of oxide with acid and bases, and you could get any acid or any base. So yeah, this is sodium oxide with sulfuric acid. As you see, it forms a salt and water. And this is magnesium oxide, salt and water again. And this is silicon dioxide, which is acidic, so it reacts with an alkali. Phosphoric acid. And this is sulfur dioxide. And sulfur trioxide. Again, you shouldn't memorize these, you should just know how the equation works. It forms a salt plus water. And for aluminium, it can react with acids, like in this equation. We can also react with bases, like in this equation. And for this last one, this is kind of an exception because the water is on the left-hand side, and that's because a complex is formed. Okay, so that's done. Please like and subscribe to the channel. And yeah, see you.